Missed a couple people, but hopefully they'll join up soon here. So just to sort of recap from where we left off on Wednesday, we were starting to talk about instruction scheduling. So we talked about how selection works, where we're essentially just pattern matching from the IR instruction or instructions to the assembly instruction or instructions. And so once we actually have our assembly instructions, we need to schedule those instructions, or we can schedule those instructions to execute on the actual hardware. So the actual hardware consists of a CPU, and those CPUs tend to have pipelines so that we can execute more than one instruction at a time, or we can do some part of the instruction execution at a time, and that has 5 stages, which are fetch, decode, execute, memory, and write back on a simple computer. So if we're talking about more complex machines of today, most of the Intel-based processors will have 10 plus stages that all do slightly different things. This might be that we have a stage for adding versus a stage for multiplying, etc. But we'll have generally more stages than what are shown here. And we want to make sure that these are all as full as possible at all times, especially the first 3 stages. So the fetch, decode, and execute, we want to basically always be doing one of those things on a new instruction every cycle. So every nanosecond, we want to be fetching a new instruction. We want to be decoding the previous instruction that we fetched, and we want to be executing the instruction that we just decoded. And so we want to keep this as full as possible without having any stalls. So if an instruction can't execute, it has to stall and wait until it can. So that might mean that it's waiting for the result from a previous instruction. Often that is a load from memory. So if we have to load a value into the registers, any instructions that use that register value are going to have to wait for the value to actually be placed in the register from memory. And so that tends to be a big source of pipeline stalls, which means that we're just sort of waiting around for the next value to be available. So we want to basically try to reorder the instructions so that it fits well into this model, so that when we are executing, we're always able to fetch, decode, execute, and sort of have something in those stages at all times able to execute and not having to stall for something from a previous instruction. And this gives us sort of a short window, right? If we have to load something from memory, we have this mem operation that happens here. The next instruction can use that as part of its execute, but it's got to be done at that point. So we want to make sure that, any memory operations that we have to use, we might have, loaded it here and actually have to use it here. And that way we know that it's actually going to be in a register by the time the instruction is able to execute. This gets further complicated by newer hardware. So because of the fact that we've had so many transistors in excess for so long, now most processors or a lot of processors will be super scalar, meaning that they can have more than one instruction per pipeline stage. So this is what roughly that would look like. So instead of having a single fetcher, now you have 2 fetches. You have 2 decoders, you have 2 execute units, you have 2 memory units, you have 2 write back units. And we can use both of those units in every cycle. So we can fetch 2 instructions, we can then decode those 2 instructions, execute those 2 instructions, and do any memory operations and write back that went with those instructions. And then in the next cycle, we can fetch 2 more instructions. So theoretically, this allows us to double our performance, right? Or cut our performance, our runtime in half, right? Because we can now do 2 things at once. But this means we have to have more independent things to do. Because now we just talked about stalling. So if we have a load in one of these instructions, now because we're trying to do 2 things at a time, the instruction that was going to use a load where it might have been 3 cycles away before is now just 1 cycle away. So if we had something basically the fourth instruction that was being executed used the memory from the first instruction. Now that first instruction is still in the same place, but the fourth instruction is actually executing on the second cycle. So with superscalar, we need less dependencies. We need to have things further spaced out so that there's a little more time, because we're trying to do things twice as fast. We need a little bit of extra padding, a little extra buffer room in order to actually be able to execute things twice as fast. We need to make sure that we have time for things to be loaded from memory so that we can actually execute the instructions we want to execute. So that's superscalar processing. And what these do is exploit instruction level parallelism to provide better performance. So, for example, if we're doing, x plus 1 or x equals x plus 1, and we're doing y equals y plus 1 at the same time, these are two completely distinct operations, right? They don't rely on each other, assuming we don't have any aliasing on x and y. These are two completely different operations. And so we have instruction level parallelism because this likely translates to something like, we would have load x. Move to the next page here. So in assembly, this would likely translate to let's change things. There we go. We'd have load x, add x, comma 1, store x. And we would have load y, add y1, store y. So if we have these instructions here that we're actually going to execute, this is not the most efficient way to do this, right? Because these are independent. We can actually reorder these instructions in order to make this more efficient. So what we can do here to basically exploit the fact that this processor is going to run the way it does is do maybe load x, load y, add x1, add y1, store x, store y. So now, if we think about this in terms of the superscalar processor, we can load x and load y at the same time, right? We can fetch that instruction, decode, execute, and that will allow us to do both of those operations at the same time since they are independent. We then have sort of the most amount of time between loading them and adding. In this case, we don't have a lot of other independent stuff to do in the meantime, unfortunately, because we're just doing two operations. But it's possible in more complex code, we might be able to sort of fit more stuff in between here so that by the time the loads are done, we're ready to do the adds and we can move on to that execute stage and do both of the adds at the same time. And then once the adds are done, then we can store these back into memory. And generally the way that processors today work is that stores can sort of be done lazily. We can, put them into a queue and basically wait for the memory to finish storing that value. And while we're waiting for the store to finish, basically assume that this memory location has been updated to that value. So that can go pretty quickly. So then the only thing we're waiting on here are the loads, basically. And the rest of this can execute in superscalar. Whereas if we left it the same way as it was before, we would have to do this load. Our next instruction, the add, we could fetch and decode it, but we can't actually execute it until the load is finished. So we'd sort of fetch, decode, get to the execute and memory stages for the load, and then we would be stuck waiting for that add to be able to execute, and we would be stalled until that add can execute. Now we can continue doing, the sort of fetch and decode for the store and the next load, but we wouldn't be able to execute those until this finished. So we're still considering this to be sort of in order, making sure that we do things in the right order here. So if we don't reorder the code, we can't do multiple things at a time. We can't exploit the fact that this hardware can do two things at once. So that's sort of the crux of the problem here, is that we're trying to exploit the fact that our hardware is more complicated that we can do more than one thing at once. We can have instruction level parallelism. And so we want to find ways to reorder the code to exploit that instruction level parallelism where we have independent operations that can be performed at the same time by the hardware. And we want to structure the code that comes out of our compiler such that that is readily available and apparent to the hardware, that it can sort of execute all these things at the same time. Any questions sort of so far on the setup here? Okay. So let's consider a sort of more complicated example then. So I have this code for SAXP, which is single precision X plus Y. So this is a common kernel in high performance computing. It's usually used as like a GPU computing example. So all it does is we have an int(n) coming in, the number of things we're going to work with. We have a float a, which is the ax. We're going to do ax plus y, where x is a vector and y is a vector. So we're multiplying a by every element of the vector x, and then we're multiplying the vector x by a, and then we're adding that result to a vector y. So we have two arrays coming in. These are all floating point values. And what we're going to do here is, this is not super properly nested, so I'm just going to add this back in for sanity's sake. So we have y of I is equal to a times x of I plus y of I. If we look at the assembly code here, we have this first part is just the loading the value of I, comparing the value of I to n. So n is, this is n here. I is negative 28 RVP. Like sort of mark these off. So load I, compare to n, and then jump if it's greater than or equal to. So we're just inverting the condition there. It's basically jumping over the code to exit if we are not, if the condition isn't true. So exit the loop if I is greater than or equal to n. And then here, sort of the meat of the code. So here we're going to load x of I believe. We're loading x of I, loading I itself, and then loading a. Then we're doing the multiply. So this is the a times x of I here. Then we're going to load, again, we're going to load I. We're going to load a y. And then we're going to do the add. We do the store back into memory. So this is the y of I equals the result. And then we're going to load I again and increment it. And then we're going to store I again. So that's roughly what this assembly code is doing. So the first thing we want to think about is what is dependent on, which operations are dependent on each other, and which ones can we reorder here. So you can sort of think about this either from the assembly code, or if you just want to look at the C code, that's fine as well. It's going to give you a couple minutes to think about what operations are dependent here, which ones can be reordered. So go ahead and look at that. Just take a minute or two here to sort of parse through this and think about what is dependent, what can be reordered.
Sir, quick question.
Uh-huh.
After the multiply instruction, why are we loading I again?
This is unoptimized code. So it is not set up necessarily to prevent that sort of a extra load there. But you are
Okay.
correct. We could probably, because of the fact that RAX doesn't change here, we
Yeah.
could get rid of that instruction, and that would be
Okay.
fine.
Okay, I just want to make sure I wasn't missing something.
Nope.
Thank you.
Yes, this is redundant. And same here, actually. This is also redundant. Okay, so then what do we think? What is either in terms of the C code or in terms of the assembly code, what is sort of dependent on each other? What do we have to do in order?
So, like, those loads at the beginning, like load X, load I, load A,
Mm-hmm.
the multiply instruction is dependent on those loads.
Right, right. So the loads themselves are not dependent on each other, but the multiply coming after it is dependent. So this is, dependent on previous loads. And we should have the same thing here, right? This is also dependent on previous two loads. What about the move SS here? So is this dependent on anything else? This is sort of the right back of y of I is equal to the result.
So it's going to be dependent on the add.
Yeah.
Multiply.
And then of course the stuff at the end here. So this update here, loading I, incrementing I, is not dependent on anything per se. Storing I is going to be dependent on, or sort of dependent on the previous loads of I, right? So we can't update I to a new value until the previous values of I have already been used. So there are different dependencies we might run into, basically like read after write, write after read, write after write. So these are your standard pipeline hazards from computer architecture. And here this would be we have to maintain that this write occurs after these reads occur, so that we don't update I and then store to I. However, if we wanted to, as long as we used a different register, we could theoretically move these two instructions to anywhere else, because the add and the move that occur, sort of the load and the add here, could happen anywhere while we're executing this code. They don't necessarily have to happen right at the end before we jump back to the beginning of the loop. So dependent operations. So basically, each iteration. So each add is dependent on the loads before it. Each multiply is dependent on the previous add. Each multiply is dependent on the loads before it. Each add is dependent on the previous multiply. Each store is dependent on the previous add. What about individual iterations? Is the iteration for I equals 0 dependent on, or is the iteration for I equals 1 dependent at all on the iteration for I equals 0?
Nope.
No. So each iteration is independent of the previous iterations, sort of modulo I being updated, right? So the I++, if we sort of got rid of that, then everything is independent. So given that, what could we do to increase the scope here for instruction scheduling? Like, could we make this better in terms of the sort of amount of instructions that we have to reorder somehow?
Would it be loop unrolling?
Yeah. So loop unrolling here specifically could really increase the amount of independent instructions we have, because right now we're just looking at one iteration. If we were looking at more iterations, then we would have more independent work that can be reordered. That's more loads that can sort of be done up front, and then sort of do the multiplies and the adds while we're once we're done waiting for all the loads to happen. It gives us a little more room to work. And in general, so loop unrolling is for this example. And then in general, we could also use function inlining to increase the scope for instruction scheduling. So that's another technique that we've talked about that moves instructions would allow us to sort of do things in parallel, because we have more stuff sort of clumped together. So I do want to walk through sort of a more complete way of doing this. So here I have the same code that has just been labeled with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 to indicate the instructions. We could actually, if we wanted, so Rupam noted that the load to I is redundant a couple times, so we could get rid of this, simplify the instructions a little bit, and I will adjust this so it's not too bad. So we have 10 instructions, just looking at basically how do we figure out what is dependent on other stuff. So what I'm going to do is we're going to make a dependency graph here. So if we have basically each node in the graph is going to be an instruction, and we're going to label those instructions, or we're going to connect these edges or connect the graph by what instructions are dependent on the other instructions here. So if we have, basically, a node for each of these first 4 instructions, and I set these up the wrong way. We can think of the fact that basically, like, this move, this move, this move is all needed to do this multiply. So we have XMM is the output, and this is an x86 instruction. So this is basically like multiply what's already in XMM by this new stuff and put the result in XMM. So this instruction is dependent on 1. And so 4 is dependent on 1. And that means we're going to add an edge in this graph from 1 to 4. So basically just going to draw an edge from the instruction that the next one is dependent on, or the instruction preceding this, to the instruction that is dependent on it. So this indicates in a graph that 1, this move SS, or this, that basically 4 is dependent on the result of 1. So 1 has to happen before we proceed to 4. We do the same thing for 2, since 2 is loading into RAX, and RAX is used in this instruction. So we're going to have an edge from 2 to 4 as well. And same thing here, since we're loading into RCX, and then RCX is used in 4, we're going to have an edge from 3 to 4. Okay? Any questions with this so far? Okay. So then from here, we have to look at the next instruction. So we have this load into RCX from 24. We do have to be a little careful here in that we basically want to ensure that we have independently named values. So we may also want to basically rename RCX so that we don't have a dependency from this instruction to this instruction. So we're sort of going to do this assuming that we have properly renamed things This is roughly the same as like what we would do for SSA form. So because of the fact that like 16 RBP going into RCX is a different value than 24 RBP going into RCX, we can assume that these two are not dependent, assuming that we have enough registers to sort of make that true, that we don't have a dependence here. So now we're going to have a 5 and a 6 instruction. 5 is going to be independent of everything else here, right? It's just loading from a new memory location. Nothing is changing RBP here. So because nothing's changing RBP, this is completely independent. So this actually is a root of the graph that we, could start the instructions from here. Like if we wanted to load this value into a different register, we could definitely move 5 up to the very beginning, and it wouldn't change the semantics of the code. Then we have 6. So 6 is going to be dependent on 5 because 6 is using RCX, which we just loaded here. It's going to be dependent on the instruction that loaded RAX, which is 2. So we're actually going to have a dependency from there going up to there as well. And then we're going to have a dependency from 4 to 6 because 4 is doing this multiply on XMM. We're not reloading XMM. So again, this is a complicated x86 instruction where we're writing over the result, but we're also using that result. So here we would have, this dependency setup where 6 is dependent on 5, 4, and 2. So we have these edges moving to 6. And then we have the 7 instruction. 7 is going to be dependent on 6 because 6 is changing XMM, and then we are reusing XMM here, storing it into these values. So this would also be dependent on knowing RCX and RAX, and so the move here for 5 is going to go to 7, and 2 is also going to go the whole way up to 7 because that's where we loaded a value into RAX. So 7 is dependent on those 3 things as well. Then we have finally this add into EAX. EAX in x86 is the same as RAX. So we'll have 9 here just to make it a little easier. That's going to be dependent on 2 because it is using the value from EAX. And then we're going to move that value into RBP, which means that we have 10 here. Or sorry, that was 8. Sorry, skip the instruction. That was 8 there. And 9 is going to be dependent on 8. And then the jump is actually just, completely, jumps are sort of a weird thing where it is completely independent, theoretically speaking, right? There's nothing that is feeding into that jump instruction. However, we do want to make sure that the jump instruction sort of happens at the end of the block. If we move the jump instruction, it's going to completely change the meaning of our code because we're not going to execute any of it. So we do need to make sure that the jump instruction is at the end, which means that we want to make sure that the last things that happen are leading into that jump instruction. So we'd want to make sure that sort of 7 and 9 are both done before we jump out of this code. So the final sort of operations that we're performing in this block have to actually happen. Okay. So I know this is a bit confusing looking. It's a complicated graph, but this is essentially how the compiler is going to schedule these instructions. So then what it would do after this point, and I forgot to share this with you, sorry. Here's the link to this in case you want to look at it. I will update these other 2 or sort of splay it out a little bit more into separate slides after class. So once we have this this setup where we have our sort of directed graph here, what the compiler will do is then, based on the semantics of the hardware, it will label each edge with the latency that we expect that instruction to take. or not necessarily the latency we expect it to take, but the number of pipeline stalls that we expect to happen between, say, 1 and 4. So this is our weight for the graph, is basically how much stalling are we going to have to do if I immediately execute 1 after I execute, or immediately execute 4 after I execute 1. So in this case, because we are loading from memory, we might assume that this could be like 10 cycles of stalling, because we could say as sort of a rough estimate that maybe we can get this from the cache, and that this wouldn't take any more than 10 cycles. And same thing for 2, since that's another load, from all the edges going from 2 to 3, etc. We might be able to say that that's about 10 cycles that we would expect to stall. Whereas maybe from 4 to 6, because 4 to 6 is just a multiply into an add, we might say that that's only 1 cycle, because the hardware usually doesn't have to stall if it's doing an arithmetic operation and then another arithmetic operation. And same thing if we're going from 6 to 7, we might label this as a 1 as well, because we are going from an add into storing the result of that add, and that's usually a pretty quick thing. So we essentially just label these. These numbers are 100% made up right now that I'm putting on this graph. Not 100%, but it's somewhat realistic, but it's also just making up a number here for sake of example. But the compiler would have some hardware-specific information about how long these operations might take. Basically, is what we're looking at here. So it wants to know, how long will we have to stall before the next operation can execute. And then what it does is we basically start from the roots. So anything that doesn't have an incoming edge could be the first thing that we execute. So we could start from the roots of 1, 2, 3, and 5. So 1, 2, 3, and 5 are all the nodes in this graph that don't have an incoming edge. So they don't have an arrow pointing to them. And we can choose one of those things to schedule. So in this example, what the compiler ended up scheduling was 1. So it schedules 1, and then it looks for other nodes in the graph that are ready. So ready meaning that either it doesn't have an incoming edge, or any incoming edges have already been scheduled. So like we can schedule 4 once 1, 2, and 3 have been scheduled. We can schedule 6 once 5, 2, and 4 have been scheduled. But we have to have all of those incoming edges, the nodes coming in, have to be scheduled first before we can schedule that node. So the compiler just goes through, picks those nodes. We could pick 3 at this point because we don't have any incoming edges to 3. We could choose to schedule 5 next if we wanted to. And then finally, we could schedule 2 because that's the last remaining thing that doesn't have an incoming edge. And then from here, we can choose to schedule, at this point, 8 only has the incoming edge from 2. 4 has all of its incoming edges scheduled, so we could choose to schedule 4 or 8 at this point. And then once we schedule 4, we can choose to schedule 6. So essentially all we're doing here is just going through the graph, looking for nodes that have not been scheduled, and all of the incoming edges have been scheduled, or that there are no incoming edges. Sort of trivially satisfies that constraint. And we can continue to schedule nodes, and each time we schedule one of these, that's the order that we generate these instructions in. So that's what the compiler is doing sort of under the covers. And what it's trying to optimize for is sort of the lowest number going to that node. So we want to schedule things sort of as far in the past as we can if there is a big latency. So, for example, if we had, let's say we knew that we could do this, these loads a little faster, then we would definitely want to schedule 1 first because we have the longest path to the end going through 1. So we want to optimize for the fact that 1 would have 10 plus 1 plus 1 to get to the last node in the graph. So this is sort of our sink here, is the last node. That's what we're looking to get to through this graph. We want to minimize the latency between the node that we're scheduling, or sorry, maximize latency from the node that we're scheduling to the end of the graph. So we want to do the things that are going to have the most stall latency first, so that hopefully that stall latency is minimized as we execute this code. Okay? Any questions on that? Okay. So as an alternative to this, one of the things I'd like to go over in this class, because it's a mistake that has been repeated multiple times, and it always seems like a really good idea, and then it turns out to not work super well in practice. So as an alternative to superscalar execution, a lot of what people have, or a number of different projects have proposed what's called packed instructions. So this is what shows up in VLIW, very long word instruction computers, and EPIC, explicitly parallel instruction computing. So if you want more information about this, by the way, if you get a chance to talk to Dr. Ratvik, he worked on EPIC at Intel, I believe, for some amount of time, and can tell you a little bit more about this. And so what this does is, thinking about this sort of superscalar pipeline, we have, you know, instructions, or maybe thinking about this code here. So we have this setup basically that we load something, we load some stuff, and then we do an arithmetic operation on the stuff that we loaded. We load some more stuff, and then we do an arithmetic operation on the stuff that we loaded. Again, we load some more stuff, and then we do some arithmetic on what we loaded. So people have come up with this idea that basically, instead of having independent instructions that we reorder within a basic block, instead, we could have bundles of instructions that get executed at the same time. So for example, we might have an arithmetic instruction and a memory operation that sort of get packed together, and then the hardware executes those as a single unit. So every time the hardware does an operation, it executes an arithmetic operation and a memory operation and a comparison. And it can do all three of those at the same time. And then the idea is that the compiler will find groups of those instructions to execute as a VLIW instruction and form them into packs. So this has been tried a few different times, basically, you know, trying to look at the code, find where we can pack these instructions together, form these units, and then schedule them that way. The problem is that the scope, or especially the static scope available for instruction scheduling, is often way too small to form efficient packed instructions. So even just looking at the code that we just talked about, if we have something that does a memory operation, an arithmetic operation, and a comparison, we don't have any comparisons in here. So that comparison sort of part of the instruction is always going to be empty. We only have 3 arithmetic instructions as compared to the very large number of other instructions. So even if we get, especially if we get rid of the redundant loads here, we have, you know, 3 arithmetic instructions. We have 1, 2, 3, 4, 5, 6 memory instructions. So we're going to have, you know, 3 instructions that, or 3 VLIW instructions that don't have an arithmetic or a comparison operator. And so it's going to be difficult to basically fill these instruction packs with the number of instructions that we want to be able to execute at the same time. Even if we loop unroll, we're still going to have an imbalance of 1, that we don't have any comparison instructions, 2, that we, you know, don't have the same number of memory and arithmetic operations to have execute at the same time. So again, this has been tried a couple times. It hasn't worked out. It is possible that, you know, maybe someday in the future we find a better algorithm for doing this. But the main issue is that this is, in fact, an NP-complete problem, right? So we can't figure out what the best ordering of instructions is unless we try it. So this labeling of like solving this graph for the shortest path is not NP complete. It's not that difficult to do computationally, but that's because we're using a heuristic to assign weights to these. In reality, what we actually have to do to find the best possible schedule of instructions is to try all the possible schedules of instructions and see which one executes the fastest on our hardware. And that is difficult to do, one, because trying every possible ordering of the code is very time intensive and expensive, or simulating it is very time intensive and expensive. But also just the fact that there are an exponential number of different orderings of instructions that we could try, especially in a large application that really explodes in terms of the number of things that we would have to attempt to execute to figure out what is going to be the fastest possible ordering. So we do some instruction sort of static scheduling, but what we really fall back on nowadays is that high performance processors use what's called out of order execution, or OOO execution. So this is used to increase the scope of instruction scheduling in the hardware. So here what happens is the hardware sort of maintains a window of instructions that can currently be executed. So it will continuously fetch and decode instructions. Once it has fetched and decoded instructions, it keeps basically a table of all the instructions it has fetched, and checks to see, can this instruction be executed? And as soon as we can execute an instruction, we execute it. So it does basically what we were just talking about, but in hardware instead. So it has, all of these instructions there. It waits for their dependencies to be resolved, and then it executes the next instruction that it can execute. Instructions are still committed in order. So we still wait to make sure that, the instruction has, has gotten the correct results, especially if we do something like branch, and sort of speculatively branch. So some of you may have heard about things like Spectre and Meltdown in the news. So processors do speculative execution these days. So we might speculate that this jump is going to happen, or here we might speculate that I is still less than n, so that we are going to continue executing this code rather than jumping out of the code. But that is speculative. So we're going to speculate n times correctly, and then the last time we're probably going to speculate that we are going to execute the loop again, and we're going to have to basically do some work and then throw it out. This is more for an architecture class, but I think it's worth bringing up just briefly here. So we have speculative execution that may need to be rolled back if it's found to be incorrect. However, we do want static scheduling a little bit to generate programs that are amenable to out-of-order execution, and second, for low power environments. So like your phone is probably not doing out-of-order execution. Your desktop or your laptop is, because that's a higher powered processor. It's assuming it's being plugged in. But generally out of order is pretty power hungry, because we are keeping a big table of instructions that's sort of constantly being accessed. So the circuit is being fired quite frequently, or powered quite frequently. So it tends to be that we need very sort of large power hungry structures to do out of order execution. And so in low power environments, we do still need static instruction scheduling in order to deal with the fact that we don't have the out of order execution. And the last thing included in the notes here is basically what we just talked about with the example is list scheduling. So this is the most common algorithm for instruction scheduling. It uses 4 steps, which is 1, rename the values. This is just the SSA form translation. 2, build the dependence graph. So that is, basically assigning these edges so that we have an ordering of instructions that have to execute. Assigning priorities. So again, this is the heuristic part of it, where we say, what is the latency going to be from this instruction to the next one? And then finally, iteratively select an instruction to schedule it. So we already talked through this process already. So that's instruction scheduling in a nutshell here. I know there's sort of a lot here in terms of the hardware. This unfortunately sort of mixes a lot with computer architecture in that, it's highly dependent on what the actual hardware is going to do. And it's harder to dive too much deeper into this just because it ends up being an issue of like, what is the actual semantics of the assembly language that we're looking at. So if we look at instruction scheduling on x86 versus instruction scheduling on ARM, we're going to have totally different results in terms of what we have to do and what instructions we can reorder, which ones we can't. But the basic idea should be there, right? That we have dependent instructions, we have independent instructions. We can reorder independent instructions, and we want to try to do so to eliminate pipeline stalls. So are there any questions overall on this process? Okay, in that case, we will pick up with register allocation on Wednesday, lab time tomorrow to hopefully finish up or get closer to finishing up the optimization lab. And just keep in mind that and the other lab is going to be due at the end of the semester. So that's on the 28th. So please keep, plugging away at those. Feel free to schedule EI with me on my calendar. If you need help with them, I'm happy to meet with you outside of class, or obviously I'll be around tomorrow to answer questions while you're working. But yeah, lab time tomorrow, and then we'll talk about register allocation Wednesday. I will get out project ideas sometime, hopefully today or tomorrow, so that you have time to think about it. And then I want us to sort of choose projects on Wednesday so that we have those ready to go. So the next couple weeks, so after this, we'll be working on projects and sort of meeting on an ad hoc basis. So if there is a need to talk about some specific topic for your projects, we can meet and talk about that. But otherwise, I'll basically we'll have some time to work through working with LLVM and doing something interesting, hopefully. So I will see you on Wednesday, or see you on tomorrow for lab, and then see you Wednesday for a lecture. So have a good day, everyone.
Sir, can I have a research question?
Yep, go for it.
So I've been trying to like check the